Hello, I'm Tyler Goodman. I'm the front-end developer for the Composable project. Here's our website, which was built in React. We have a simple landing page here. If you head over to our build page, you can see functionality to generate functions, and this pulls data off etherscan.io and pretty much just gives you the ABI for any contract. So we can pull things such as compounds contract and put it here, and then we get all their functions. So how this works is you just choose a function, you can edit its parameters, you can add more functions, and then once you're done doing this, you can finalize it, and then you come to this page, which is kind of just like a receipt of everything you had just built. You can have your wallet connected, in which case you can send these transactions to the Composable protocol. And the front end will generate the bytecode that it will send. And just to show you what that looks like, you can click send here. And this is what will end up getting sent to the Composable protocol, where it will execute this function based on what we had built previously.
Hello, everybody. My name is Justin. I'm going to tell you a little bit about the back end of Composable. I'll begin by running a simple test which demonstrates the functionality. So basically what we have is a contract which executes arbitrary function calls on other contracts. And the way we do that is by specifying a certain encoding standard, which we've provided with the project. So what you see with a normal encoded call is the function selector followed by the call data. What you have with Composable is instead you start with the address, the function selector, and the size of the call data, and then you add the call data. And the way that it's encoded makes it so that you can always know where your dynamic arrays end in a list of dynamic arrays. So it opens up a lot of possibilities. So we interrupt the function selector mapping phase by using a fallback function in Solidity, inspired by the Diamond contract standard and proxy contracts and multi-sig wallets. It's something that's already in use today. So yeah, by using this assembly, we have a very small contract that can do arbitrarily many calls up to the limit of memory, of course. And yeah, there's going to be some interesting uses for this. In particular, we think it could save compound protocols, governance contracts, a lot of gas by not storing proposals into storage, but instead storing a Merkle tree composed of the KCAC hashes of each 32 bytes of a composed string of call data, including the addresses, selectors, sizes, Ethereum values, Ether values, and call datas. By doing that, you could potentially save 10 words, 10 storage slots, which is way better. You're basically taking these you're taking all these arrays, you're shrinking it down by a substantial amount. So